Another application of first order differential equation involves mixture problems. So at the end of this presentation, we should be able to apply the solutions of first order differential equations on problems involving mixture. So when we say a mixture, this is a solution which is a combination of a solute and a solvent. So once we mix the solute and the solvent, forming the given solution. So on this type of problems, once there is a certain solution that is coming in on a certain system, the amount of solute can be determined at any instant of time, or if we want to determine what should be the concentration of the solution. Okay, so the concentration of the solution at any instant of time, we'll be able to determine it as well. So in solving differential equations involving mixture problems. So to start with the definition or the working relation that we are using for mixture problems, it states that the amount of substance at any instant of time is equal to the rate at which the solution is going in, minus the rate at which it is going out. So as you can see here, x would correspond to the amount of the substance at any instant of time. So the rate at which this amount changes over a period of time is equal to the difference on the concentration or the input concentration, multiplied it with the input flow rate, minus the product of the output concentration to that of the output flow rate. And in this given differential equation, we could resolve this one by specifically knowing what would be the concentration that is going in on a certain mixture, and the concentration is usually, this is the amount which is usually expressed in terms of a mass unit, and then with respect to the volume, the amount of the substance with respect to the volume, okay, or the amount of the substance per unit volume, that is considered as the concentration of the mixture. And then the amount or the flow rate, the volume per unit time, okay, the volume per unit time would correspond to the flow rate of the given mixture. And then the output, it's similar with that of the input concentration and with the output flow rate as well. So take note that the concentrations can be taken out as x all over v, wherein x would be the amount of the substance at any instant of time, with respect to the volume. Volume of the it could be a mixture or it could be a pure liquid, but v here would be the volume of the liquid, okay, not the container that it is holding it. And then the volume of the liquid, okay, or the volume of the mixture on a certain container can be computed or can be determined using the initial volume, okay, the initial volume plus the difference between the input flow rate minus the output flow rate, multiplied it with time. So as you can see here, the container could overflow, okay, the container could overflow if the input flow rate is higher or faster as compared to the output flow rate. And on the other hand, the mixture inside a container could be emptied if the output concentration would be greater than that of the, or the output flow rate is greater than that of the input flow rate. Okay, so those are just the things that we need to remember. So for mixture, so that is the dx all over dt is equals to C in times Q in minus C out all over Q out. And then the concentration is X over V. And then V would be equal to V initial. Okay, so plus Q in minus Q out multiplied it with time. So to better understand the applications of first order differential equations or in terms of a mixture problem, so let's have our example number one. So a tank contains 200 liters of fluid in which 30 grams of salt is dissolved. So brine containing 1 gram of salt per liter is then pumped into the tank at a rate of 4 liters per minute. The well mixed solution is pumped out at the same rate. So find the number of grams in the tank at time t. So let us try to draw a certain container here or a tank. So we have for our given, so let's say I have a tank, and then initially, so the tank, so it has a fluid inside. Okay, and then it says there that the tank so contains, okay, so let's say 200 liters. So initially, so the tank has 200 liters, and then in which 30 grams of salt is dissolved. So initially, there is a certain amount of salt that is dissolved inside the tank, and that amount is equal to 30 grams. So initially, so the if X would be the amount of the substance, and that substance is equivalent to salt. So initially, there is 30 grams inside that tank. And then a brine containing 1 grams of salt per liter is then pumped into the tank. So something is flowing into the tank, something is flowing in, and that is called the brine. So when we say brine, so a brine is a combination of a salt and a water. Okay, so it's a mixture of salt and water, and it has a concentration or an input concentration that is a 1 gram of salt, so per liter. Okay, so per a liter of a mixture, so there is a 1 gram of salt. Okay, so for every a liter of brine, there is a 1 gram of salt in it. And then the brine is pumped into the tank at a rate of 4 liters per minute. So therefore, the input flow rate, so that would be 4 liters per minute. And similarly, so the same amount of mixture is pumped out from the tank. So our Q out so would be 4 liters per minute as well. So our task this time is find the number of grams in the tank at time t. So for our solution, so what is required then is we need to find, so what would be the amount, okay, so of the substance, in this case that is salt, for a or at any instant of time. So for our solution, so if X would be the amount of salt at any instant of time, so we could use our differential equation. So we're in dx over dt, so is equals to C in times Q in, okay, or CI times QI then minus C out, Q out. Okay, so that would be our general formula. And this time around, so let's substitute. So we have our CI, QI, and Q out. But what we don't have here would be the C out. Okay, so the output concentration is actually equal to X, multiply it with V. And then just like what I've mentioned during the discussion, so V is equivalent to the initial volume. Okay, so plus Q sub I minus Q sub O multiplied it with T. So our C sub out then, so would be X all over, so initial volume, so based from the given, so we have 200 liters, then plus, so the rate that is coming in and going out would be the same, so 4 minus 4, and then times T. So 4 minus 4, so that would yield to 0, and thus our output concentration is equivalent to X all over 200. So X all over 200. So and thus we could already substitute all the given. So dx over dt would be equal to, so our input concentration is 1, and then the flow rate is 4. 1, then the flow rate is 4. Then minus, our output concentration is X all over 200, multiplied it with our output flow rate, so which is 4. So multiplied it with 4. And that's giving us, so dx all over dt, so would be equal to 4. So minus, so 4 over 200, so that is the same as x all over 50. And then as you can see here, so it resembles something, okay, so about a linear equation. So dx over dt, and then transposing negative x over 50 into plus x all over 50, so that would be equal to 4. And thus forming an equation on under a linear differential equation. So from here, we can see that our P of t is 1 all over 50, and then our Q of t would be equal to 4. So recalling the formula, so for linear differential equation, so we need to get first our integrating factor mu of t, so that is equal to e raised to the integral of P of t dt. Then e raised to the integral of 1 over 50 dt, or simply e raised to t all over 50. So t all over 50. And then our general formula for linear differential equation, so would be mu of t. So multiplied it to where it is linear. So this time around it's linear in x. That is equal to the integral of Q of t mu of t dt. And that is e raised to t over 50, so multiplied it with x, and then Q of t is 4, mu of t is e raised to t all over 50 dt plus c. And from here, we could integrate. So if we're going to integrate this one, so u is t all over 50. So du then would be dt all over 50. Or our neutralizing factor would be 1 over 150, or just simply 50. Okay. So this would give us, so e raised to t or over 50, so times x would be equal to, so 4 times 50, then e raised to t all over 50 plus c. Or simply, so x e raised to t over 50 is equals to 200 e raised to t over 50 plus c. And then, so we are to find what would be the value of c. So to determine the value of c, so we have to take a look at our initial value. So at time 0, so initially, so the concentrate or the amount of the salt that is present within the mixture is 30 grams. So 30 grams of salt is initially dissolved on a 200 liters of fluid. So 30 grams. So that is when x is 30, so our time would be equal to 0. Or when time is 0, so x is 30. So 30, and then e raised to 0 is equals to 200. So e raised to 0 over 50. So plus c. So giving us, so 30. So this would be 1. This is 1 as well. So 30, then minus 200 is equals to c. So c then is equals to negative 170. And thus, so giving us x e raised to t all over 50 is equals to 200 e raised to t all over 50 minus 170. Or multiplying everything by e raised to negative t all over 50. So giving us, so x to be equal to 200, then minus 170 e raised to negative t all over 50. And thus, so giving us the amount of the salt that is present at any instant of time, so would be equal to x is equals to 200 minus 170 e raised to negative t all over 50. So this would be the amount of salt for whatever values of t. And that is what we are finding in this particular problem. So the answer would be x equals to 200 minus 170 e raised to negative t all over 50. So let's proceed with another problem. So this time around, so we have a 120-gallon tank, so holds purified water. So salt water with 1.5 pounds of salt per gallon, so leaks into the tank at 2 gallons per minute. The mixture in the tank is constantly mixed and it flows out of the tank at 3 gallons per minute. So how much salt would be in the water after 10 minutes? So let's try to visualize our problem. And then we're just going to plug in all that are provided on the problem. So let me draw a container here. And then it has a 120 gallons of purified water. Okay, so let's say this would be the water. So we have the initial volume, so which is 120 gallon. And then it was not mentioned, so whether there is a solute within, or it's not even mentioned that it is already that it is a mixture. So since initially, so we are talking about a purified water or a pure water, so therefore initially there is no substance or there is no solute, okay, so that is present initially on the water. And then for some time, so a salt water enters in. Okay, so a salt water flows into the tank. So with a certain concentration of salt, so which is 1.5 pounds. Okay, so pounds per gallon. And then the salt water that leaks into the tank, so would have a flow rate of 2 gallons per minute. Then the mixture in the tank is constantly mixed. Okay, just to tell us that there is a mixture, or there is an equal concentration on the different parts of the container. So nothing settles down, but the solution, or the solute, okay, so it's dispersed evenly, so within the mixture. But the difference this time around, so on our first problem, so we have the same flow rate, but in this case, the flow rate at the output, so is a bit higher. Okay, so we have the Q out, so which is equal to 3 gallons per minute. As you can see here, uh, the flow input flow rate is 2 gallons per minute, and then the output flow rate is 3 gallons per minute, the volumetric flow rate. So since the output flow rate is faster as compared to the input volumetric flow rate, so there is a possibility that after some time, the container, okay, the uh, the tank, okay, so holding the mixture of purified water and salt water, so will be emptied in the future. But our task this time is, so how much salt would be in the water after 10 minutes. So we are tasked to find, so if we're going to use x again as the amount of salt at any instant of time, so after 10 minutes, that is x10. So what would be the amount of salt that is present after 10 minutes? So to resolve such problem, so we will be using the same formula, that is dx all over dt is equal to Ci Qi minus C out Q out. So dx over dt is equals to, our input concentration is 1.5. So while our input flow rate, so that is input volumetric flow rate, is equals to 2. Our output is a bit faster, is 3, but our output concentration, that is x all over, so the formula that we are using before, that is C out is equals to x all over initial volume, so plus Qi minus Q out multiplied it with T. So our initial volume is 120, and then plus Qi is 2 minus 3 multiplied it with T. And afterwards, so multiplied our Q out, so which is 3. And thus dx all over dt would be equal to, so 1.5, so times 2 would be equal to 3. So minus 3x all over, so 122 minus 3 is negative t. So giving us again a linear equation. So dx all over dt, so plus 3x all over 120 minus t, so would be equal to 3. So our P of t, so is equals to 3 all over 120 minus t, and our Q of t is equals to 3. And thus, our integrating factor mu of t, so would be equal to e raised to the integral of P of t, so that is, so I could just move out 3, and then dt all over 120 minus t. So our u here would be 120 minus t, so du then would be equal to negative dt. So we should have a neutralizing factor of negative 1. So thus, we have e raised to negative 3, and then we have ln of 120 minus t. Or simply e raised to ln of 120 minus t raised to negative 3. Or 1 over 120 minus t raised to 3. So for our mu of t. So now that we have our integrating factor, so our general formula so would be mu of t. So multiplied it with, so it is linear in x is equals to the integral of our q of t, so which is 3, and then multiplied our mu of t, or that would be, let me write the formula. So q of t, mu of t, dt. So mu of t would be, so x all over 120 minus t raised to 3 is equal to q of t is 3, and then our mu of t so would be 1 all over 120 minus t raised to 3 dt. So I could rewrite this one as x all over 120 minus t raised to 3. So would be equal to, I could move out 3 there. And then the integral of, so 120 minus t raised to negative 3 dt. So again, so our u here is 120 minus t. So du would be negative dt. So our neutralizing factor is negative 1. So that, okay, so let's integrate. So x all over 120, so minus t raised to 3. So that would be equal to, so we have a neutralizing factor of negative 1. So I'll have a negative 3 there. And then, so 120 minus t raised to negative 3. So using power formula, so I'll have 120 minus t. So negative 3 plus 1 would be negative 2 divided with negative 2 plus c. So, and thus, so giving us, so x all over, so 120, so minus t raised to 3, then would be equal to 3 all over 2, so 120 minus t raised to 2 plus c. And then initially, so since this is a pure water, so when time is 0, so x is 0 as well. So if x is 0, so the left hand side is all 0 already. And then we have 3 all over 2 times 120 minus 0 raised to 2 plus c. So giving us 120 squared, so times 2, and then 3 divided with our answer. So we'll have c to be equivalent to negative 1 all over 9,600. So substituting that, so I'll have x 120 minus t raised to 3 is equals to 3 all over 2 times 120 minus t squared. So minus 1 over 9,600. So multiplying everything, so by 120 minus t raised to 3. So giving us x to be equal to 3 all over 2. So multiplied it with 120, so minus t. Then minus 1 over 9,600, so multiplied it with 120 minus t raised to 3. And this would be our general working equation. So for the amount of the substance at any instant of time t. But our task is to determine, so what would be the amount of the substance after 10 minutes. So when t is equals to 10, so what would be our x. So we're just going to substitute it. So 3 all over 2. So multiplied it with 120. So minus 10. So minus 1 over 96. And 120 minus 10 raised to 3. And that would give us, so 3 over 20 times 110. So minus 1 over 96 times 110 raised to 3. So giving us, so 3 all over 2, so times 110 minus 110 raised to 3 all over 9,600. So giving us a 26.35. And the unit, so will be pounds. It's pounds per gallon. So we have 26.35 pounds of salt. So will be present on our mixture. Okay, so after 10 minutes. Okay, so that's another set of problem. And lastly, so we could have our last problem, so which is about 120 gallon tank, so which can hold a purified water at a maximum capacity. Then salt water with 3 pounds of salt per gallon, so leaks into the tank at 5 gallons per minute. The mixture in the tank is constantly mixed and it flows out of the tank at 3 gallons per minute. So if the tank was holding 100 gallons of purified water, so how much salt would be in the water at overflow? So similar with the previous example, so let's draw our tank. And then, so let's identify the given. So initially, so it can hold a purified water. However, there are two volumes that are present here. So initially, so we have a 120 gallon tank. So meaning the 120 would be the maximum capacity of the tank. So that would be the capacity. So capacity, so that would be equal to 120 gallons. And then based from the problem, so if the tank was holding 100 gallons of purified water, so again, so 100 gallons of water, so it means 20 gallon, okay, so to fill it up. And since that is a pure water, so initially salt is not present, so initially. So how about the input concentration? So our input concentration of salt water, there would be 3 pounds. Okay, so 3 pounds per gallon of salt. And then for our input flow rate, so we have 5 gallons per minute. And then for our output flow rate, Q out, so that is 3 gallons per minute. As you can see here, so the input volumetric flow rate is greater than that of the volumetric output flow rate. So therefore, there is a tendency that our tank so will overflow. So since the input flow rate is faster than that of the output flow rate. So our solution, or what we are to find, would be, so how much salt would be in the water at overflow. Okay, So what would be the uh, okay, so what would be the amount of salt at time t? So we do not know when will it overflow, but it will overflow. So when our final volume, okay, so reaches 120 gallons of mixture. So for our solution, so we will be using the same formula. So dx all over dt so would be equal to ci qi minus c out q out. So dx over dt then so would be equal to our input flow rate is 3 and then qi is 5 gallons. So minus q out, so that would be x all over. So our initial volume is 100 plus, so qi is 5, or sorry, qi is 5, then minus 3 times t. And then multiplied it with our q out, which is 3. Or rearrange or simplifying this one, so dx over dt would be 15 minus 3x all over 100, so plus 2t. So transform it into the standard form. So dx all over dt, so plus 3x all over 100 plus 2t is equals to 15. Our mu of t then would be equal to e raised to 3 the integral of dt all over 100 plus 2t. So our u is 100 plus 2t. So du would be 2 dt. So our neutralizing factor then would be 1/2. Or simply e raised to 3 all over 2. And then this would be ln of 100 plus 2t. Or e raised to ln of 100 plus 2t raised to 3 over 2. Or 100 plus 2t raised to 3 over 2. So mu of t, so times x is equals to the integral of q of t, mu of t dt. So mu of t is 100 plus 2t raised to 3 all over 2 times x is equals to our q of t is 15. So 15, so 100 plus 2t, so 3 all over 2 dt. So again, so our u is 100 plus 2t, so du is 2 dt, and our neutralizing factor would be 1/2. 100 plus 2t raised to 3 all over 2 times x is equals to 15 all over 2. So for our neutralizing factor, and then 100 plus 2t, so 3 over 2 plus 1 would be 5 all over 2 all over 5 all over 2. Or sorry, so that would be plus c. So 100 plus 2t raised to 3 all over 2 times x. So 15 all over 2 divides 5 all over 2. So 2 and 2 would cancel out. 15 divides 3 would be 3. And then 3 times 100 plus 2t raised to 5 all over 2 plus c. So multiplying everything by 100 plus 2t raised to negative 3 all over 2. So giving us x to be equivalent to 3. So 5 over 2 minus 3 over 2 would just be 3 times 100 plus 2t. And then plus c, multiplied it with 100 plus 2t raised to negative 3 over 2. So if we are to get, again, so what would be the value of C? So initially, the solute is 0. So when time is 0, so x is 0 as well. So 0 is equals to 3 times 100 plus 2 times 0. So plus C. Then 100 plus 2 times 0 is to negative 3 over 2. Or just simply 0 is equals to 300. Then plus C times 100 is to negative 3 all over 2. Just simply negative 300 is equals to C. And then divide it with 100. So raised to negative 3 all over 2. Or just simply, so negative, or C then would be equivalent to square root of 100. So this is the same as negative 300, so make it positive, so 100 raised to 3 over 2. So C then would be equivalent to 10 raised to 3 is 1,000. So we have negative 300,000 for our C. So X then would be equal to 3 times 100, so plus 2T, then minus 300,000. Multiplied it with 100 plus 2T raised to negative 3 all over 2. So we are to find, so when will it overflow? Okay, so to find when will it overflow, so we can determine, okay, so we already know, so what would be the volume, okay, so to make it or to overflow, and that is when the volume is equivalent to 120 gallons. Okay, so 120 gallons, so that would be the time that it will overflow. But to determine the amount, so we need to find, so what would be that time. So we have our formula before that our initial volume is equals to the volume, the volume at any time is equal to the initial volume, and then plus the difference on the flow rate, so Qi minus Q out, multiplied it with T. So from here, so we could have the volume at any instant, so minus the initial volume, so divide it with the flow rate, so that would constitute a time. So the time here, so would be when will be the time that we will have a overflow, and that is when V is equals to the maximum capacity, that is 120 minus the initial volume is 100 gallon, then our flow rate, so we have the Qi, so which is 5, then minus 3 for our Q out. So T then would be, so 20 divided with 2, so that would be 10 minutes. So to determine the amount of the salt after or during the time that it overflows, so we can now substitute T to be equivalent to 10. So 3 times 100, so plus 2 times 10, minus 300,000 times 100 plus 2 times 10 raised to negative 3 all over 2. So x then would be equivalent to 3 times 120. So minus 300,000, 120, and negative 3 all over 2. Or that will be, so 3 times 120 minus 300,000 times 120, so raise it, or sorry, 120, then raise it to negative 3 all over 2. Negative 3 all over 2. And giving us a 100, correct? 131.78. So x would be 131.78 pounds of salt. So that is the amount of salt that is present on the mixture. So during the time that the mixture within the container overflows. Okay, so those are examples in solving mixture problems. Good day.